Morning, everybody. Hopefully, you've already done your little experiment with your 3-point bonus activity of what factors affect like your charge stored on your plate with its plate distance and area and the field and so on. So it's very helpful to do that one before you look at this little video. So if you haven't done so, if you're going to do that lab, I highly recommend you do that lab first and then look at this capacitance video and PowerPoint. It's going to make sense of everything. So here we go. All right, so there's old Paul E. Tippins. So what we're looking at today is going to define exactly what capacitance is for a parallel plate capacitor, and it works the same if you just roll up this parallel plate into a roll, which you commonly see what capacitors are. They are just parallel plates, they're just rolled together. It's a more efficient design of less space, but they're all parallel plate capacitance. Well, not everything has to be parallel plates, but for capacitance, normally that's what we're talking about. So we're going to talk about a dielectric constant today, which is going to increase the capacitance of a capacitor and what that does in terms of voltage, field, intensity, and capacitance. And finally, we're going to also look at the potential energy stored. How do you store the most energy possible in capacitors? Here we go. All right, maximum charge on a conductor. So what happens is a battery establishes a potential difference that pumps the electrons from the ground to a conductor or vice versa. So the battery makes that potential difference. It could be on your car instead of the earth, but it all works the same. To put a charge on something. Now, there's a limit to how much charge you can put onto that thing. Just like on the Van der Graaf generators, you could only put so much charge onto that thing, and you hit a limit that you can't fit any more charge on it. It ionizes the air, and it shoots right off of the conductor. So there's a limit of how much charge you can store on things, okay, without it leaking off. So it has a capacity to hold a certain amount of charge, okay? So that's the first important thing about a capacitor. It has a capacitance for holding a certain amount of charge for leaking. So this capacitance is defined as a ratio of that charge per volt. So in one of your graphs, you should have found out the graph that has the charge on the Y and the V on the X, as you change your voltage what happens to charge, you should have found it to be a linear line. And the slope of that is indeed the capacitance of a capacitor, which is its ability to store charge, okay, per volt. That's what a capacitance is. Ability to store amount of charge per volt. Okay, so units of this are coulombs per volt. Okay, or the special unit is going to be farad here in a moment, but for right now, it's just your charge per volt, which is coulombs per volt. Okay, so farad is the unit of a coulomb per volt. It's the same thing. It's another way of saying coulomb per volt. And so 1 farad would be the capacitance if you have a 1 farad capacitor, and we have some up at school, unfortunately none of us are up there. It's a very, very, very large capacitance. That means you can store a whole coulomb per every single volt. If you had 2 volts, that'd be 2 coulombs. If you had 3 volts, that would be 3 coulombs, and so on. So 1 farad capacitor means it's got a very high capacitance. It can store a lot of charge per volt, okay? So more than likely, most of our capacitors are much lower than regular farads. So we're in the micro, and you notice even the charges stored in your experiment the other day was down in the pico. Pico is 10 to the negative 12th. Picofarads is a normal amount of capacitance for a small capacitor. So when you have 40 microcoulombs of charge placed in a conductor with a potential of 8 volts, capacitance is, it's your 40 divided by 8, but remember it's times 10 to the negative 6 on that thing. Or you can leave it alone, leave it there, and you end up with your 5 microfarads, which is a pretty common thing to do. It's easier than writing 5 times 10 to the negative 6 farads. Okay, so the capacitance of the capacitor would be a 5 microfarad capacitor. So on a sphere, rules are different for a sphere than they are on a flat plane because the fields are going to be different. But even on a sphere, you have a certain capacitance. Now this doesn't pop up much on the AP2, but it will pop up on your electrodynamics if you're taking that test about a certain capacity to store charge on a on a round ball. So at the surface, we already learned that the field is just found by the constant, which K, 9 times 10 to the ninth, the charge you can put on there per square. So that's any round object, as long as you're on the outside of that thing. And the potential from that point charge, or you're outside of that ball, is a KQ over R. And since the 9 times 10 to the ninth is really 1 over the 4 pi the epsilon, which is the permittivity of free space, we can substitute that back in to get the Q over the 4 over the pi and the epsilon the R. And then capacitance, because it's this charge per volt, we can substitute that in for the voltage, hint, hint. And so we go with the Q over the Q, so the Q's disappear, and you end up with this little hoodad here. This is for a sphere, though, not parallel plates. This is for a sphere. So to find the capacitance to store charge, or the capacity to store charge, it's just 4 pi epsilon times the radius. So if you double the radius, what happens to the capacitance? Correct, it doubles. Very good over there. So what is the capacitance of a metal sphere at the radius of 8 centimeters? Make sure you make that 0.08, and you just plug and chug it in right there, and bam, there you are. 8.9 times 10 to the -12 farads, which is 8.9 picofarads of capacitance. May not seem like a lot, but you can't store a lot of charge per volt on a round sphere of that size. Okay? So the capacitance depends only on the physical parameters, the radius, not determined by the charge or the potential. We're going to find the same thing with your parallel plates. Your capacitance is dependent on the physical characteristics of your device, whether it's round, whether it's a plate, 2 plates, and so on. It's true for all capacitors. Okay, so what's the charge is needed to give a potential of 400 volts? Well, we already know the capacitance of the thing. We already found it. It's 8.9 picofarads. So if you want to find out how much charge you can have on the potential, all you have to do is solve for the Q, and bam, that's how much charge you can put on that conductor. So had we been at school, what we would have done is measured the radius of a round sphere of our Van de Graaff generator. And we're going to find out in a little bit what the ionization energy is to break down this and get a spark. Or by measuring this spark, we can actually get an idea what the potential is. And if you know what the potential is at that time of the spark, and you know what the capacitance is, you can go back and find out how much actually charged that there actually was on that ball. Alrighty, so the farad and the coulomb are extremely large units. So we use a lot of micro, nano, even pico when we talk about capacitance. So maximum charge can be placed on a sphere that has a surface, a circle surface, 1 meter in diameter. So that's a ½ meter in radius. Okay. So if you want to find the maximum charge onto that thing, well, this is for the field you can have on there. So here's the problem. This air is going to break down at 3 million volts per meter or newtons per coulomb. Remember, that's the same thing. Okay, at 3 million, that's when you have a round sphere that's going to break down the air. Charge is going to come shooting off of that thing. Okay, and since it's 3 million volts per meter, that's how you can determine from the length of the spark, how many meters the spark is, what that potential would have been. Okay. So we have our whatever electric field is. It's a 3 million. We got the radius, we got your K, and bam, there's the charge that was actually stored onto that thing before it started shooting sparks off of there. 83.3 microcoulombs. Okay, so it illustrates the large size of a coulomb as a unit of charge in electrostatic applications. So long story short, if you want to store a lot of charge, have a lot of area. So if you want to store a lot of charge on something, we don't have bigger balls. What we do is we add more people. The more people you have, the more area you have, and thus the more area you have, the more places you have to put charge. You can put more charge per volt on there, and you have a greater storage of charge the more people you use. Alrighty. So parallel plates, so this is the more common stuff that we use for capacitors, is the parallel plate stuff, because we can store a lot of charge on here, and the reason for that is because when you separate the charges, you make a field in between there, and they attract each other, and that helps us to store more charge, because when we take electrons off one plate, the top plate, and put them on the bottom over here, that just makes this want to attract more charges off. And so what happens is we can store a lot more charges with the parallel plate than we can with a single plate. Okay, so for these two parallel plates, we already learned the VED formula. Okay, so we learned the VED formula before the corona caught us. And so we're going to combine these two to look at, well, what kind of features on this represent the capacitance of a parallel plate system. So from Gauss's law, we had, what the field is. It depends. We're talking about the surface. And so we have parallel plates. That's why it's not a single plate. That's why it's not a 2 in there. So that's your charge density. And your charge density is your charge per area per your epsilon. Okay? And since E equals V over D, we can just set VED or V over D equal to charge over that. And voila, there's your relationship. So your capacitance is measured by how much charge you can put per volt on a material. But for parallel plates, we find the capacitance by the area and the distance between the two plates. So if you double the area, what happens to the capacitance? It doubles. Nicely done. So what if you double the distance between them? Then what would happen to the capacitance if you in fact double the distance? It's half. Very nice. It'd be half the capacitance. So by moving these closer, by making this distance smaller and smaller, we can actually put more charge on there because we're increasing the field between there. So by getting these closer and closer and closer together, they really attract each other pretty strong. If you move these apart, it takes work because they attract each other. It takes physical work to pull these apart. Well, the further apart, the less charge you can actually store on there before it ionizes there and shoots off of your parallel plate or across from here. So moral of the story is, the bigger the area, the more charge you can store per volt. Alrighty. So capacitance, you can find it by your charge per volt, or by if you knew the area of your plates. Permittivity, this means there's nothing in between here, or air's in between here. So you use a permittivity of free space, there's nothing there but air, or it's just a vacuum. It's pretty much the same number, at least at 2 sig figs anyway. Okay? So if you wanted to add something in the middle, it actually changes this value. Anything you put in the middle is going to change it from permittivity to something else, and that's where we get the K thing coming in. The K is a constant of whatever material you put in there, and we're going to call it the dielectric constant. The reason we call it a dielectric is because normally we put a polar device in here. If we put a polar device in here, it makes this, you can even put more charge onto there than what you could before. It doesn't have to be a polar. Some are non-polar capacitors, meaning it can go either way. Okay, more on that. So permittivity of free space, that's the epsilon naught, that's the 8.8, 10 to the -12th. We've talked about that before. And the relationship to the K. So that's, if we know the K is the 9 and so forth. So we tend to use that. So a couple applications to this. So some kind of microphones, you have different kind of microphones. Some work, but they all work by converting sound waves and electrical signals, but they work differently. One way is you could use it by using a capacitor. So by the sound vibration hitting one of the two plates, it changes the distance. It vibrates at higher pressure, lower pressure, higher pressure, back and forth, back and forth, back and forth. Well, that changes the capacitance back and forth. If you're changing the capacitance, that's changing the amount of charge you can store onto there. So you're actually making charges go on and off, on and off, on and off, because you're changing capacitance by squeezing that forward as you're changing the capacitance of the thing. So as you change the capacitance, you're going to change how much charge there is. That's going to vibrate the charge, which is how you get your vibrating electrical signal that you send to something else, and then later on to amplifier and to speaker and so on. But that's one kind. Another kind where we have a variable capacitor is the old tuners. The old-timey tuners where you didn't have, things weren't digital. You actually, by turning this thing, you could turn this inside of this, you have more area right across from each other. By rotating this inside, you have more area. By rotating this backwards, you have less area or less capacitance. So that's an example of a variable capacitor, because you're changing the actual area. Here we're changing the distance between the two, but here we're changing the actual area between the two, which technically changing the distance because you're going in between there as well, but the main thing is you're changing the area, and that's how you can tune into different things. All right, here's an example number 3. Plates of a parallel plate. We're going to stop right here because you only have 2 seconds, and we'll pick up with example